We're looking to find the total area between a function and the x-axis. The formula that helps us calculate area, of course, is related to the fundamental theorem, but if you've got the area wedged between two functions, which this x-axis is the function y equals 0, then one possible way of going about this is to integrate from some starting value out to some stopping value, the top function, whatever function's vertically higher, minus the bottom function, whatever function's lower. And as long as those are well defined over that entire interval, this will find the area between top and bottom. So to see what areas we're talking about, I think I would begin this problem by graphing the function, the x-axis, and make sure I see which pieces are involved over the interval from x equal 1 to x equal 4. So I've already got some axes drawn on here. Let's go ahead and graph our parabola. X squared minus 9 is a parabola opening up, pushed down 9 units, so this is the number -9 down here. And the x-axis, of course, is just the line y equals 0. It's a horizontal line. And the first question that comes to mind then is where is 1 and where is 4 relative to this crossing point? And it's very important that we know this. So I'll solve x squared minus 9 equals 0 and find the x-intercepts for that parabola. Of course, as soon as you write it down, you can pretty much see it. The x values that this function crosses at are plus and minus 3, square root of 9. So this number right here is -3, and this number right here is 3. All right. That means that the number 1 is over in here someplace, and the number 4 is just outside. So the area that they're looking for here, the region that they want the area of, would be anywhere between x value 1 and x value 4 between these two functions. So it looks like there's actually two pieces, a piece from 1 to 3 and a piece from 3 to 4. Now you could use the fundamental theorem to get each of these pieces individually. This formula also gets them for you, so I'm going to go ahead and use this formula. That first area, this first one here, would have the integral from 1 to 3. I would start at x value 1, stop at 3. The top function on this region is the function 0, so that's not too hard to integrate. And the bottom function then is the parabola, x squared minus 9. And watch the parentheses on there. This will calculate always a positive quantity, so that'll give me the positive value that is represented by this little green region down here. Now we could have just integrated from 1 to 3 the function x squared minus 9. We know that that would have come out to be negative, and we could remove that negative sign. But this formula builds that into there. This minus sign right here will make this come out to be a positive value. To that then, we will add the area between the function and the x-axis from starting spot 3 to stopping spot 4. The top function in this region is x squared minus 9, and the bottom function is just 0. So again, we could have just used the fundamental theorem, integrate from 3 to 4 the function x squared minus 9, and you know that's exactly what we're going to end up doing here. Now I'm ready to do the calculus. I'll rewrite this once just to clean it up. If I distribute that minus sign, it's a minus x squared plus 9, and this one is just the integral from 3 to 4 of x squared minus 9. Now we anti-differentiate and plug in our two endpoints. This will be equal to minus 1/3 x cubed plus antiderivative of 9 is 9x. We'll evaluate this at 1 and 3 and subtract. And then To that we'll add the antiderivative of x squared minus 9 evaluated at 4 and 3. Same antiderivatives. That's a 3 there. Minus 9x. And this will be evaluated at 3 and 4. Now we plug in all of our numbers. See, when I plug in a 3 cubed divided by 3 will be a 3 squared, so this will be a minus 9 plus